Hello everyone. Today I want to discuss a very important subject with you all. So, we know that IT has become a very integral part of our lives, especially nowadays. But the sad part is that many people don't realize the complexities and the intricacies of the systems that control it. So today, we will explore the landscape of IT together, and we will see a very high-level overview of the many components that it's built upon. But as you know, IT is a very big field, so we had to divide it into many different parts. And today, we will see the very first one. So as with anything, we need to start with the definition. So what is IT? IT is information technology, but it doesn't give us too many clues, so let's examine it word by word. First of all, we have information. If we try to define information, information is data that is organized, that is processed and understood. But a question arises, what is even data? So to try and explain data, data is divided into two categories. So we have data that it describes quantities, data that can be counted, things like 5 apples, three bananas, things like that. And we have data that describes qualities, characteristics, and properties, things like hair color, for example, things like the grades of a student. So now that we got that out of the way, we will discuss what is the second word. We have technology. So a very basic definition of technology is the practical use of scientific knowledge for a specific aim. So for our aims of purposes, so if we combine the two definitions, we get that information technology is the methods and the tools that we use in order to manipulate information and data and process it. So both data and information. So we don't make the distinction when we talk about information technology. So this is usually different from computer science, which is considered more theoretical and much more part of academia and research. So as a recap, we have information technology is the manipulation and the processing of the methods and the tools that enable us to do that. So data and information is usually expressed in IT as strings of ones and zeros. We see an example here. So now that we finished our definition, let's go through the first chapter. So the first thing that we will see is IT systems. And why is that? Because we need to know how IT wants to manipulate, how it wants to process this data and information that we have. So first of all, IT systems. What is that? So IT systems can be divided into two parts. We have the hardware and we have the software. So these two are the main components. So first of all, hardware. So in hardware, we can also divide it into several parts. So first of all, we have the computation hardware, the computation devices. So things like the CPU, the RAM, and the GPU. So these things is the crust, is the things that make it possible to process and compute the information to make it useful for us. And this is the crust of the issue. So these are the most important components of a computer. We also have storage. So where we will store our data, we need to store it so that it won't get lost and it won't get corrupted. We have things like hard drives, things like SSDs, and the much more recent NVMe. And we also have I/O devices, things for input and output, things like the computer mouse, a USB stick for input, or a monitor screen or headsets for output. And we also have other devices like a network interface card, for example. So let's focus on the CPU for a second. The CPU, and it's the central processing unit. So this is the brain of the computer. It's the thing that makes it think. So it's composed of the most important component of the modern era. It's the transistors. So transistors are semiconductors, and basically, if it lets electricity pass, it's considered one, and if it doesn't, it's considered zero. So this is the building block. It's the things that make us understand and makes the representation of data possible. So remember the strings of zeros and one that we discussed earlier. So if we combine these transistors together, we get logic gates, and the logic gates enable us to express more complex logic, things like the addition, the add, the or, and with that, we can build very strong and very complex computer architectures. So this is the, it's like, this is the process that we build upon our computers. So this is a very oversimplified view, but it serves as a basis to understand the meat of the issue. So what are the different types of hardware that we can get? So we have personal computers. So you're watching this video on a personal computer, statistically speaking, most likely. So we have personal computers, things that are designed for home use, and we have bare metal servers, things that enterprises, companies use. And we also have embedded systems. So embedded systems are very small devices that need minimal hardware, that need minimal software to function. So things like your elevator system, things like your refrigerator, if it's smart, things like smart devices, all of them, for example. So they are embedded. They need minimal electricity and minimal systems. So how do we make all of this function? So the most important tool we have to make all of this function is assembly, because we can't code with 1 and 0. So our computers understand only the strings of ones and zeros, but we as humans, we can't do all of that. We can't express those complex logic only through ones and zeros. So we use assembly. So assembly is a layer between us and the ones and zeros. It's like a language that can make it easier for us humans to interact with binary data. So ones and zeros, it's called binary data. So this is the bridge between the hardware and software. It's assembly. So let's get through to software. So for software, we will go through a journey. What are the building blocks of software? So if we boot up our system, the first thing we have is the BIOS, or the basic input-output system. So this BIOS is the very first component that is between us and the hardware. It lets us boot the kernel with a bootloader. So the kernel is the core, or it's the core of our operating system, and it needs to boot up first because it has all the syscalls necessary for us to function, for the system to function. So when the kernel is boot up, we get our operating system. So we are very familiar with these ones. We have Windows, Macintosh, or Linux-based systems like Ubuntu, or even Android. It's also based on Linux. So when we get our operating systems, things that the operating system is the middleman between us and the hardware. So when we get our operating systems, we get our third-party applications. So this is it's usually what we consider to be software. So these are our applications. So it can be like our Word, Excel, the browser, things like that, the web browser. So these are our applications. So to code or to design and build our applications, we can't code it with ones and zeros, of course, and we also can't do it with assembly, because assembly is very verbose. It's very long to code with. So we have many high-level programming languages that are necessary to build these sorts of applications. So we have like Python or Java, languages like C++ or C. these make it easier for us, coders, developers, to build applications for end users. So now that we have finished with software, we need to discuss the second chapter, which is networking and telecommunications. So now we discussed how we interact with information, how we can manipulate it and process it. But we miss a very, very important component. It's how we can communicate, how we can transfer the data. So telecommunication is the transmission of information over communication channels. So we have things like electric cables or electromagnetic radiation. So this is like the most simple ways of expressing the communication channels. But we can also build upon them. So we have things like wires, radio telecommunication, we have optical fibers, and we have also wireless. These are examples, but the basis is electrical cables and electromagnetic radiation. It describes all of these examples and more. So this is a general overview of what is telecommunication. It's oversimplified, but it serves as a good basis for networking. So networks, what are networks? So we have the IT systems that we designed, but the problem is that they can't communicate, they can't transfer data. So network basically is designing a network to communicate so that our nodes, our systems can communicate with each other and transfer the data and information. So there are multiple ways of designing networks like this. So the very first concept that we need to know is network topology. So there are many ways to design a network. So we have bus topology or ring, things like a star topology. So these are the specifics and the details. We won't get through them right here, but they're very important to know that we can design our systems with many different topologies. We also have the OSI model. So the OSI model describes how networking basically functions. So we have in the OSI model many layers, and the packets and the information that we want to transfer goes through these layers successfully through encapsulation and de-encapsulation. So we also won't discuss the OSI model in detail here because it deserves its own explanation and its own video. But the basic idea is that we have many protocols that the OSI model describes so that we can agree on the methods with which we can communicate with each other on a network. However, even if we brushed over OSI model, we need to discuss LAN and WAN. So the LAN, or the local area network, is local to the user. So it's things like your home network. So you have the router in your home, so you and your family, you are on a local area network. But there is also the concept of a wide area network. So a wide area network is the combination, is the assembly of all of those local area networks together. So the internet is an example of a wide area network. So it connects all of our homes, all of our enterprises together. So let's move on to our third chapter. So we discussed, first of all, IT systems, then networking. In this chapter, we will discuss software engineering. So we mentioned that in our IT systems, there is hardware and software, but the design and the building of software relies on very complex procedures, very complex processes. That's why we have a very dedicated job for it, which is the software engineer's job. So software engineering. To explain software engineering in detail, we need to explain what is even engineering is. So this is just my own definition. You can disagree with me on this, but I like to think of engineering as the application of science and math to solve problems in general. So when we discuss what is software engineering, it's good to say that it is the application of software to solve problems. So this is my own definition, and there are many more. So it's not software engineering is not only building software, it's also a process. So we have a process that goes through many weeks to months to build this software. So it can go through a very complex process. So we need to analyze the problem that we need to fix, then design a solution for it, and then develop it. It's the implementation, and we need a testing. We need to test it so that we don't ship something that it is broken or malfunctioning. And then when we test and we end our tests, we need to deploy it so that it will reach our end users. And then there's the maintenance phase. However, this is a very specific model. It's the waterfall method. There are many methods of designing software, like iterative approaches like agile or things like that. So the most basic one is the waterfall method, and it serves as a very basic model to show how software engineering works, for beginners at least. So first of all, so we mentioned that software engineering is a process. So the very first thing is we need a project management. We need to manage our projects so that we don't make mistakes. We need a leader, a manager, so he can plan, so he can see how the project will be created. So why is that? Why we need such a thing? So there are three things. There is a triangle that is cited very often in project management. So we have time, cost, and quality. So the balance of these three things is very crucial. So the project manager or the team in general needs to deliver a product in the most minimal time possible, with the most minimal budget and cost possible, and with the highest quality possible. But it is very hard to achieve that with the optimal approaches, with the most optimal results, so to say, because these things are constraints. So if we focus too much on the costs and lowering the budget, we risk lowering the quality with it. So it's like a paradox of choose two and leave one. So a project manager is the one who knows how to balance these three constraints. So a project life cycle, it begins with the concept phase. So we know what we are going to deal with, and then we need to plan. We need to make a summary of the tasks that we will do, the jobs that will need to be done, the people that are tasked to do things like that. And then after planning, we need to execute our plan. And finally, there is the closing ceremony so that we can liberate the resources that we had, the budgeting and the human resources that we allocated for our project. And in this project management sphere, we talk about the 4 Ps. So we need to focus on the 4 Ps. We need to focus on the people, the product, and the process, as well as the project. So out of all these 4 Ps, we need to focus on people the most, because the people is the most important asset of your project. So the people is the human resources that we allocate to do our project, for the succession, for the project lifecycle. So we need high quality people that can do their jobs, and we need to know how to allocate them. So we don't want to waste resources, we don't want to waste time, waste people's time. So we want to attribute or allocate the tasks in a very balanced way, or among different people, because life is that way. People are not the same. So the people have different levels. So we need to focus on how much people are able to do the task. So for example, we have a person that he excels in building applications, web applications. And we have another one who excels at building mobile applications. We can It will be very counterproductive to give the one that excels in mobile applications a web task. So we need to know how to allocate these tasks for each one. So this is it for project management, a very high-level overview of what is project management. Next up, we have the conception phase. For our conception phase, there are many frameworks, but before that, we need to conceive. We said that we need to design the solution. So conception phase is how we conceive the solution, how we anticipate the implementation phase will go. So we have many frameworks to do so. And the most important one and the most famous one is the UML, or Unified Modeling Language. In the Unified Modeling Language, we have many diagrams, and these diagrams serve as the basis of the description of how our project will go. So the most important diagram here is the class diagram, and it describes how our entities will interact. But the devil is in the details, so we will leave it here. And maybe we will get into another video in how UML functions in more detail. For the software architecture, we need to also focus on the architecture of our software, because there exists many. For example, we have the client-server architecture. So, for example, if we have a web application, we can design it in a way that we have a client-server architecture. For example, the client will be the front end, and where the user will interact with the page in his browser. And the backend will be hosted in our servers, and he will be called the server. And we will then have a client-server architecture. We have another architecture which is the N layer. So it's like an extension of the client-server model. So we can call the client-server architecture a two-layer architecture. And the N layer is simply adding more layers to the architecture. So we have clients and servers, and each one serves as the client of the next one. We have also the master-slave architecture, where we have a master dedicated to the management of the cluster and the slaves that do our work, which are called sometimes worker nodes. So we also have peer-to-peer architecture. In the peer-to-peer architecture, all nodes, all entities are equal to each other. So each one is a client and a server in the same time. So there is no difference between each one. We also have the event bus architecture. So it tries to decouple the publisher from the subscribers. So we have a publisher that publishes information in topics, for example, and we have subscribers that subscribe to a topic. So when we have new information in that topic, new events, we can fetch them. So the event bus tries to decouple the subscribers from the publishers. We also have many other architectures, and they are not mutually exclusive. We can use many architectures in the same project if we want to. So for the development phase, and this is the most famous stage of software engineering. So it's the implementation, it's the code. So we can design web applications in the development phase. We can also design mobile applications, and the much more outdated, but it's still in fashion, the desktop applications. So there exists many frameworks and many tools that help us design these applications. So in the web sphere, we have things like React for the front end, React, Angular, and for the back end, we can have also things like Spring Boot. So it has a very large ecosystem. So things to take away is that we can build websites, we can build mobile applications and desktop applications. So the code part is generally easier to do because there is many resources on the web that help you do it along the way. So while we're here, it also helps to know how to interact with databases because it's easy to forget, but we are inside the realm of IT, so we deal with information. And in most applications, if not all of them, we will need to store information and data. And to store that, we need a database. So in almost all kinds of applications, you will need to know how to store data in a database. We also need to know how to use APIs and to interact with them because as we mentioned in the networking chapter, we need to transfer data. And APIs or application programming interfaces serve as the middleman to enable that transfer. So this is a very oversimplified view of what is development, but it serves as an introduction. So the frameworks that you will use will give you more detail into how to construct, how to build these applications. So next up, we have quality assurance. So we mentioned that we need testing in the waterfall method, for example, and it's crucial in all methods to be exact. So we have things like unit tests. We have many types of tests because we need to have a test coverage that covers all of our projects. So we use many tests to do so. We have unit tests that covers the basic building blocks of our code. So things like the individual functions, the individual code that we run. So these tests test the unit, test the foundational units of our program. We also have integration tests that tests the application as a whole. So, for example, the unit tests may be able to test functions in a package. Let's say, for example, things like monitoring the weather. So unit tests will test the functions of fetching weather data. Another unit test will compute the weather in an instance or in an instance of time. However, the integration tests will test the functioning of the application as a whole. So it will test if we can compute the weather, for example, in an interval of time or Monday through Friday, things like that. So we want to test all of the units at the same time. However, there is another kind of test which is end-to-end testing. So in end-to-end tests, we test how the user will use our application. So we simulate his behavior and we simulate the clicks of the buttons and how he will interact with our application. This is the basis of the end-to-end test. And there exists more for sure. So we need to also discuss automated testing versus manual tests. So the most intuitive way to do these tests is the manual way. So the manual approach is to, when we end our development phase, then we will execute each test manually ourselves, the developer here. But a more smart approach and a more efficient approach is automated testing. So if we let the tests run each time we deliver new features, it will eliminate the human factor and it will improve the speed of the process of development. And then we can assure that our product is of high quality. This is what quality assurance. So quality assurance is not specific to software engineering, but it's a very helpful concept in software engineering because quality assurance is more general in engineering in general. So it helps factories to manufacture things like vehicle parts, things like that. So in that scenario, we have to assure the quality of the vehicle parts. But in the software engineering realm, we need to assure that our software, that our code is running properly. This is what quality assurance is. So this is the end of part 1. IT is so big that we can't integrate all of this in one single video because it will be longer than 2 hours. The next parts, we will discuss more chapters with you, and then I hope that this high-level overview will help you have a more general map, a roadmap of how you can think about IT. So see you next time.